Greetings everyone and welcome back to the bench. Today I'm going to take the JAT501 amplifier prototype board and hook it up to a power transformer based supply. Now when I designed that amplifier, I used my bench supply, which is regulated and goes to a maximum of plus or minus 32 volts. This amplifier is designed nominally to operate at plus or minus 35 volts. So I wanted to see how it's going to perform with a transformer of the proper voltage rating. Apologies for not having a video up in a while. Just have a lot going on. I have a lot of video subjects I want to cover, so certainly not for a lack of having any subject matter to talk about. Probably about 6 to 10 videos I could make on different subjects. Matter of fact, I have 3 amplifier boards in. I just got another one in. It's one of those 2.1s. You know, it has a stereo channels and a subwoofer channel. Somebody sent that in to me, so really appreciate that. So I'd like to get one of those at least going here pretty soon. Also, a shout out to my Patreon supporters. I do appreciate your support, especially now that Google AdSense is not really paying much anymore. I don't know if it's just my channel or it's just the way things are going, but not making a lot off the commercials anymore. I had one Patreon supporter send me $100. So wow, that's really going above and beyond. I really do appreciate that. And of course, everybody who watches my videos. Okay, so digging through my junk box, I found this power transformer. It has a secondary winding of 56 volts, or measuring from the center tap to the outer connectors, 28 volts. Now that is a no-load voltage rating. And if this transformer has about a 10% load regulation, that would be ideal because it'd be around 50 volts, or from the center tap, 25 volts. To each side of the winding there. So why am I selecting a transformer of this value when the 501 amp here needs a plus or minus 35 volt rail? We have to remember that the transformer is measured at an RMS voltage. So you have the AC waveform coming out of the transformer, and then it gets rectified, so now you have these pulses like this, and of course it gets filtered with the capacitors. And with no load, those capacitors are going to charge up to the peak, not the RMS. It's going to charge up to the peak. So you're going to have a much higher voltage. Plus there's no load on the transformer, so instead of the 25 volts, it'll be more like 28 volts. And well, there is some losses in the diode's forward voltage drop, but we'll end up with around plus or minus 38 volts with no load. Now with a moderate load, it'll pull that down a little bit. You'll notice that you'll get a waveform like the solid line here. And at this point, the capacitor is getting charged up again. So this voltage will be somewhat lower, but it'll still be quite a bit higher than the RMS value. And the level of this voltage depends on the load. At heavy loads, it can pull the voltage down significantly. But the point I'm making here is when you're going out to select a transformer for your amplifier, so like I said, this needs plus minus 35 volts. You don't want to run out and buy a transformer that has a secondary that's rated from the center tap to the outer connectors of 35 volts, because after you rectify and filter it, you end up with the plus or minus 45 volts or something like that, which could exceed the limits of the amplifier. And at no load, it could be as much as plus minus 50 volts or 100 volts across the rail, which is quite a bit higher than we want here. So what about the current rating, or another way to say it, the volt amp rating of this transformer? I don't know what this one is, but from dealing with transformers, I can kind of guesstimate what this is. It's probably a 120 to 150 volt amp transformer. And my personal criteria for selecting a transformer is to make it double the amplifier's maximum clean output. So if my amplifier can put out 60 watts into 8 ohms, the transformer should be about 120 volt amps. And that's nothing set in stone. It's just my personal criteria for selecting a transformer. So what I'm going to do is test this amplifier with 8 ohm loads, do continuous and dynamic tests to see what the output is. Also going to test at 4 ohm loads, and this amplifier can put out probably around 100 watts into a 4 ohm load, but I'm not sure that I would make that with this transformer because I would need a higher volt amp rating and able to do that. But we'll try it anyway and see what happens. Okay, so this is the basic circuit I'm using. I'm not saying this is the ideal supply. This is just the parts I had laying around. This transformer has 2 primary windings for connecting in series, so you get 240 volts, or you put them in parallel for 120 volts. It also has some other secondary windings, but the main windings, they have the heavy wire. This came out of one of those all-in-one type stereos. I think it was rated like 100 watts or something like that. So the power for the amplifier was these windings right here. And we'll run it through a diode bridge and use these capacitors. The value I'm using is 6800 because, it's the ones I have here on the bench. So I've rigged it up here. I have a bridge and, like I said, the capacitors. Now the last video I made, I was running this thing in Class A, so I have to reset the bias down for normal Class AB use because it was probably set to be biased at like 1.5 amps or something like that. And I don't want to do that at the normal operating voltage. Class A voltage has to be somewhat less because the heavy amount of heat that would be produced. Okay, powered up the transformer. I'm measuring across the rails here, getting 75 volts. So that would be a plus and minus 37.5 volt on the rails. I do have a bulb limiter in series which might steal a volt or two. When I measure the primary, I do get 28 volts at no load, so, or in other words 56 volts across the secondary winding there. So that's what I would expect. Okay, measuring the AC voltage across the secondary, it's at 56 volts. So like I say, from the center tap to the outer connector of the coil there, it's 28 volts. Okay, I have everything connected up here. Still have the bulb limiter in the circuit. I have the source signal coming in. I have a 1K resistor across the input here, just in case if I turn off my source here, I don't want potential for oscillation, which could draw heavy current and blow something up. One thing I would like to mention at this point is when you build an actual power supply, I very strongly encourage putting fuses after the main filters on each rail. 3 or 4 amp fuses. If you use it with 4 ohm loads, with this amplifier, probably 4 amp fuses. Fast acting. And yeah, you heard me correctly, after the main filters. The reason for that is if there's an oscillation or something, it gives an opportunity for the fuses to protect the amplifier from having heavy current dumped from these main filters. If you put it before the filters, then there would be no protection from that. As they say, it's the transistors that end up protecting the fuses, but You know, with good quality transistors, the fuses should protect the amplifier. Okay, so just a quick test here. I still have the bulb limiter in circuit. Just a quick, make sure everything's working right. Okay, well, now what I'm going to do is put the non-inductive load resistors in the circuit, take out the bulb limiter, hook up the scope, and we'll get some power measurements. Okay, I have everything hooked up. Make sure the mains is not going to short anything. The dual supply output here is not going to short anything. I cap the outputs with these wire nuts so that they don't short together. I have the two 4 ohm non-inductive loads in series for 8 ohms. Of course, the bulb limiter is out of the circuit. And monitoring the voltage, amplifier at idle, so it's drawing around, not drawing, but the output voltage is about 73 volts. So we'll see what this thing does. Okay, we're pointed at the scope here. Let's get a measurement. There's the waveform. We'll crank this up. There's clipping. And you can see the waveform bouncing because that's beating with the line or mains frequency. So we'll tune that out and get a power measurement. So 20.9 squared divided by 8, 54.6 watts. But here's the thing. See, when I turn this on, 63 volts. It actually drops lower than my my scope, so we're getting less than plus minus 32 volts. So maybe we need a transformer with a higher initial voltage because we're falling below our plus minus 35 volts. But at any rate, I'm going to set this up to do a dynamic power test, see what we get. So what you're looking at now is the dynamic power test. So what I had to do is set the scope up for a single shot capture. So what that does is when the scope detects a signal presence, it'll actually start measuring it at that point. That allows you to capture the single event, making it very easy to capture the data you want. So what's happening, the signal starts, and you can see it starts at a higher level and kind of shrinks down. So what I had to do, I had to play around a bit and find the point where it's not clipping here. I'll show you that momentarily. So I had to fiddle with that and find the point where it's not clipping when the signal starts. But as the signal plays, the filter capacitors discharge and you start seeing this ripple, and that's the supply frequency ripple, actually double at 120 hertz, because it charges up the capacitor and the capacitor's discharged slightly and then it gets recharged again, so you start seeing that ripple. So as I zoom in here on the waveform, you can see it's clearly clipping. And let me zoom out a bit and scroll over. Let me zoom out. It's easier to move over that way. There's the beginning, so now I can zoom in on that. See, it's just starting to clip. The more we get to the beginning of the signal, you see it's not clipping. Yeah, I could have homed it in tighter even, but Yeah, I got at least a few cycles of not clipping. And it starts out lower. That's just a function of the music player. So here is when the signal starts, you can see that it's not clipping. So what I need to do now is find the RMS value of this waveform. I can't use this number. That is looking at the entire signal. That's not usable. So let me play with the cursors here and get a voltage. Well, I stand corrected. This number is actually giving me an accurate representation of what's on the screen, because when I moved it around, especially where the signal drops out, you can see this drops down to millivolts, and that's in the millivolt range. So yeah, I'm getting a good representation of the data here. And let's put this back at the start. 23.43 is the number I used. So when I square that, divided by 8 ohms, I get 68.6 watts dynamic power. Now I'm testing at 1 kilohertz. And the reason I'm doing that, I'm screwing up my settings here. The reason I'm doing that is because it's easier to set this up and you can visualize what's going on better. I could test it at a lower frequency. I would just get fewer cycles because, you know, the waveform's a lot larger. Of course, it's really not a function of the amplifier. It has everything to do with the filter capacitor values and the power transformer. One thing I should mention is, if you run these tests, make sure that your test signal and the mains frequency are not harmonically related. Because if you're testing at 30 hertz or 60 hertz or something like that, and your line frequency is 60 hertz, well, you could get inadequate readings for your continuous and dynamic test, because the waveform could be in step with a peak. So you might be seeing more power than you can actually get, and that would be an invalid measurement. So when the frequencies are not harmonically related, or at least your test frequency is many times higher, you can see the peaks and valleys properly and get valid data. Okay, 4 ohm time. Got the 4 ohm load connected. Crank this into clipping. See, we're drawing a lot more current. Those really bounce around. So we'll tune out the clipping and stop the signal, because my little resistor is going to get really hot. Tell you what, why don't I hit stop on the scope? Okay, so we'll just say 17 volts squared divided by 4. I'm getting 72.25 watts. And wow, that's a lot less than my bench supply. This transformer is just totally inadequate for the job, especially with 4 ohm loads. And I also checked the rail voltage, really sagged. It started at about 73 volts sitting idle and dropped down to 57.6 volts under load. So yeah, significant voltage sag on the supply with a 4 ohm load. So let me set this thing up to do a dynamic test. Okay, so this is the dynamic power test for 4 ohm loads. You can notice how it really shrunk down. That transformer is pretty inadequate for the job. Of course, you have larger ripple as well. So let's zoom in a bit. Other way. Go to the front of the thing here, front of the waveform. Start of the signal. Right, there it is. We'll move over here. So we're getting 20 point something. We'll just say 20. I don't need a calculator for that because you square it 400 divided by 4 ohms. 100 watts. So the dynamic power with this transformer and capacitors I'm using is 100 watts. So what dictates this roll off here? Well, number one, the capacitor value. A larger capacitor value will have a longer time constant, so it's going to discharge slower. And secondly, the transformer. You know, a better suited transformer wouldn't sag as much. There will be some sag, but not this much. And of course, with larger capacitors, this ripple will be smaller because you have to take your maximum clean power at the bottom of that ripple, because you can't use the top, because at some point in the signal you could be clipping on that bottom part. And that's one reason why some of these high-end power amplifiers have huge amounts of capacitance. Gives them a nice long time constant of higher dynamic power range. It could go through a longer bass note in music, where with this arrangement maybe a bass drum kick. And you also get smaller ripple as well. And of course they'll tend to use pretty hefty transformers as well, where this smaller transformer is just not going to cut it. Imagine with the stereo amplifier driving 4 ohm loads, this thing's really going to sag. It's just not going to cut it. Well, I do have this toroidal transformer here. It's a pretty nice sized one. Oh man. Well, I do have this toroidal transformer, a pretty hefty one. The only problem is it has 4 secondaries and they're all like 10 or 11 volts. So even if I combined them, I'd only have around 22 volts. It's just inadequate for this amplifier. So I'm considering rewinding this. These toroidal type transformers are better. And, with the correct wire, I should have excellent load regulation. And I'd get much better performance than I do with this setup. So yeah, considering rewinding this thing. Well, there you have it, testing the JAT501 amplifier on a typical transformer type power supply rather than a regulated one. And you can see it's very important to have a good power supply for the amplifier to meet its performance specs. And I would expect around probably 65 watts into 8 ohms and around 100 into 4 ohms. And we're quite a bit off, especially with 4 ohms using this transformer. But it just goes to show you how important the power supply is. That'll do it for this one. Thanks for watching. Oh, there's the buzzsaw, kitty. There's the buzzsaw baby. What was that? Yeah. Don't drool on my saw. You rust it out. Make rust spots on it. We got some birds. 3 eggs. Robin eggs. We'll have to see how these progress.